Okay, so this is week 10. And so this week I'm just going to finish off with some more results. Okay, limit theorems related that's related to the central limit theorem, and then we will look at characteristic functions. Right, I think until next week we are already should be done with the syllabus. Okay, then you can do your revision and get ready for the test on week 13 and week 14. All right. Okay. So today, just to complete the theory part on theorems related to central limit theorem. So we have the following. This one is called the law of the iterated logarithm. Okay, iterated logarithm means log n, right? You do the log twice. Okay, that is meant by what is meant by iterated log, right? So the result goes like this. Okay, so we're just going to look at the theorem and skip the proof, right? So it basically says that if you have a sum, right, that's made up of ID simple random variables. Now here the simple random variables mean that your random variables take only two values. It's like a Bernoulli random variable. Okay, for example, you have a Bernoulli type kind of random variable. For example, if you have random walk. If you have random walk, then every step is actually a simple random variable, right? Because in a random walk, so you basically you have one with some probability p, and you move to the right, right? So this is moving to the right. This one is moving to the left, right? With 1 minus p probability, all right? So you basically just have something like two values, okay? You could also have you could also have some other values, right? But the simplest one is your random walk, okay? Move to the right, 1. Move to the left, -1. Okay. So then, so basically you can think of this as a random walk, right? You start from the origin. Then every step, so you can move either to the left or the right, right? So this sum is basically its position after n moves. Okay, so you can see that it's in this case, if you have this distribution, its mean and variance is 1, right? Because over here the expectation is basically 1 p plus -1 times 1 minus p, right? So this is basically let me see. This is minus. Oh no. So this is not actually. Let me see. So it's the sum. Sorry. The sum is. Let's check this. So this is and how come it doesn't go to 1? Okay. It's p times 1 plus -1 times 1 minus p. So that should be p minus. Okay, right. So it has to be a symmetric random walk. Okay, right. So yeah. So it has to be a symmetric random walk. So you have to set it to 1/2. Okay. So then your expectation of x1 will be 1/2 times 1. Then plus 1/2 times -1, right? So you get 0. Okay. So again, the variance of x1 will be expectation of x1 square minus 0 square. So this one is again the same, right? 1 times 1/2 plus, so there's a square here. So -1 squared times 1/2. So you get 1. Okay. Right. So this is okay. Yeah. So basically, it says that if you have this kind of setting, then the probability of lim sup of this quantity, okay, the sum is actually instead of normalizing by n, you normalize by square root of 2n log n. Right? So you consider this quantity. Okay. It claims that p of lim sup of this quantity, this random variable, equal to 1. Is 1. Okay, so it's certain. Now this is a little bit kind of like abstract. Okay, so what it actually means here is what it is trying to say is the following, right? So this is actually more concrete. So basically, it's saying that for some epsilon greater than 0, the probability that this quantity, this random variable, yeah, exceeds. Actually, this is a 2. Okay. All right, exceeds 2, square root of 2. You can, this basically it's just a rearrangement, right? So this is 1 plus epsilon, where epsilon is some arbitrary constant, right? So the probability of this random variable exceeding this amount infinitely often is 0. And the probability of this random variable exceeding this particular amount infinitely often is equal to 1. Now this is still a little bit abstract, so maybe I'll just sketch some diagram to more or less illustrate it. Okay, so basically it's if you have this quantity S, so this is your n, right? And here you have your Sn over square root of n log n. Okay, so you start from 1, okay, and then you keep on going, right? Okay, so every time it's basically you do an experiment, right, where you have in the first time you have x1, the second time you have x1, x2, the third time you have x1, x2, x3, right? So, and you keep on doing this. Basically, you think of it as an experiment, right? Where you basically run this experiment of a random walk. And in every iteration, right, you can compute this Sn over square root of n log n, okay? You compute this quantity, okay? And then you can plot it here. So it will kind of like move around, okay? It can definitely move below 0 because this sum, right? This is a random walk that's starting from, you're starting a random walk from 0. So after the sum, it can actually kind of like move around, right? Centered on 0. So you will get some trajectory like this, okay? All right. Right, so this is easy to imagine. Now, what it actually says here, the theorem, is that the following. So you have, let's say, a line here. Okay, and then I have a line somewhere here. Okay, and correspondingly, I also have 2 lines here. Okay. Now, this line here is your square root plus square root of 2 epsilon, right? You can see that this is basically just an expansion of here, right? I just write it like this so that it's easy to see. And this line here is square root of 2 minus square root of 2 epsilon, okay? And over here, this is the mirror side, right? So this will be minus square root of 2 plus square root of 2 epsilon. And this will be minus of square root of 2 minus square root of 2 epsilon, okay? Now, if you look at this curve, right, okay? So it is saying that this curve, so basically this refers to your curve, right? So it actually will go outside of this bound, which is this bound. This bound, yeah? Okay, this is this bound, right? It will go outside of this bound infinitely often with probability 1. So that means if you keep on going towards infinity, right, it will just keep on exceeding this bound, right? It will keep on exceeding this bound, okay, many times, infinitely often. Now, of course, this curve, right, it can actually go outside of a little bit of this thing as well, right? But here it says, for this result, it says going outside of this bound infinitely often, the chance is 0, which means it will only go outside of this bound a finite number of times, right? So towards the end, right, as you go n tends to infinity, it will just stay within this, it will stay below this bound, okay? Right? So it could cross this bound, but only a finite number of times. But after that, it just stays below it, all right, as your n tends to infinity. So this is the same, yeah. It can also go like below here, and then a little bit below, and then come back again. But going below this line is only finite number of times. Okay. by going crossing this line is infinitely often. All right. So basically, this is what the result is talking about. Right. It's just to give certain kinds of characterize the behavior of this particular random variable, right? As n tends to infinity. So it knows very well that it will just exceed square root of 2 plus this thing. So you can make this to be almost square root of 2 by making epsilon to be extremely small, right? Okay, make it extremely small. So this will basically be extremely small. Okay, so basically what happens is if you make epsilon to be extremely small, so basically it will just be like this, right? You have square root of 2 minus square root of 2. Okay, and you will see the curve going like this. You may touch a little bit. Okay, like that, right? Because as your epsilon becomes extremely small, the gap between these two bound becomes extremely small as well. So roughly you can think of the result as that the fluctuation, right? This quantity will actually stay within the plus minus square root of 2 line, more or less. Okay. It won't go out. It will not go outside of this bound. Okay. Okay. So this is just to fill up the part on the theory. So we are not doing much with this theorem. Yeah. It's just a result that is shared. Okay. Okay, so we are done with this limit theorem section. So now I'm going to go to the section about characteristic function, right? The last part. Okay, so before we talk about characteristic function, we look at something that is similar, the moment generating function. Okay, so just to refresh you, so you define a moment generating function as follows, right? So let x be a random variable with it can have PDF fx or probably mass function px. So you define like that. So this will be equal to fx, right? dx. For continuous case, and this one will be for discrete case. Right? Okay, so the x will actually depend on the. So I don't write it here because I will depend on what is the support, right? If you have Poisson, it will start from 0 and so on. Okay. If you have a binomial, it will start from 0 and end at n. Okay. So it will depend on the support of this this particular probability mass function. So some common ones include. So basically, it's just evaluating these things, right? Like for example, so suppose x is standard normal. So let's see what is its moment generating function. So of course you have to place some kind of restriction on t, right? So your t usually is, we'll look at that later, right? Usually you have some kind of restriction to t, so that this converges, okay? So let's say you have normal. So you have ETX 1 over square root of 2 pi e minus x squared over 2, right? dx, okay? So this will be, so you can do it like this. So this should be a negative. Dx, right? Okay. Just to factorize, right? And then come to here, you can solve this integral with the method of completing the square, right? So this will be x minus t. You square this, okay? You square this, you will get, we expand it, you will get this term, right? Minus 2tx. But then you will get an extra term, which is t square, right? So you will cancel off the t square, okay? So this is your complete the square method. Okay, this is a very basic method for working with quadratic forms, right? So here then you have this one you can take out. So you have e of t squared over 2. Then you have 1 over square root of 2 pi. Then e minus 1 over 2 x minus t square dt. Sorry, dx. Okay, so basically this integral will integrate to 1, and you will get et squared over 2, right? It integrates to 1 because basically this is the PDF of a normal distribution, but with the mean equals to t, right? And the variance equals to 1. Yeah, equals to 1. So of course this will integrate to 1. Okay, so then you end up with this term, right? So it will be equal to this. Okay, of course for this to be finite, so your t is basically just any real number will do. Okay, so your t will basically this t here it's better that you specify it, but it will depend on your distribution, right? Some distributions the t needs to be restricted to 1. Some of them, like this case, is okay to be a real number, right? So doesn't need to be really restricted to 1. Okay. Okay, so let's see. So once you have this, so you work out the moment generating function of this standard normal. So from here you can find its moments, right? Okay, you can find moments from MT, and there are several ways to do this. Okay, the easiest one is you use calculus. So basically, you take the derivative, right? D dt and t. Okay. So you differentiate and then you set t to 0. Okay. So you differentiate this, you get t e of t squared over 2 set to 0. So this is 0. Okay. So the So this is the first moment, right? It's 0, okay? Of course, because this is standard normal, so its mean is the first moment, so it's 0, okay? And generally, if you differentiate k times, this will be the k moment, okay? Right, so you can keep on doing this, okay? The other way is to use power series. So you can use an infinite series method, right? So you can do some kind of expansion, Taylor series expansion, yeah? So here you have, the other is to use Taylor series expansion. So you have e of d squared over 2. Now this is, you recall that you have the Maclaurin series, right? Maclaurin series for, which is a special case of your Taylor series, right? Of the exponential function is like this. So therefore, this will be 1 plus, so you think of this as one whole thing, so it will be t squared over 2 plus t squared over 2 power of 2 over 2 factorial plus t squared power of 2 3 over 3 factorial and so on, okay? And after that, you just need to check the terms, right? That corresponds to particular powers of t. So if you simplify this, you will get 1 plus t squared over 2 plus t power of 4 over 8 plus t power of 6 over 8 times 3 factorial and so on, okay? Now this, what does this mean here? So here it tells you something, yeah? Let me see, so second moment. So let me clear some space first. So basically over here, you have, if you already expand it, do the Maclaurin series expansion, you already have this thing. So basically you have t, so you have 1 plus etx plus t over 2 factorial e of x squared plus t, sorry, it should be t squared. So that will be t power of 3 3 factorial, and so on. Okay. So basically, you can you basically can read off the moments, right, by looking at the coefficients of the so if you so you can see here, right. So this is the third moment. So it's the coefficient of t power of 3 and 3 factorial. Okay. All right. So from here, you basically can just read off, right. If you read off, you will get, so this part is your term here, right? So from here, you know that it's multiplied by 1. So you know that your expectation of x squared is 1. Okay? And so on and so forth, right? So power of 4, so you will see that this will be 4 factorial. What is 4 factorial? 4 factorial is 24. So basically you have you can put a 4 factorial. So if there's an 8, right? So but you put it with 4 factorial, cancel it back and divide by 8. Right? So this will be your fourth moment. Okay, so this will be 3. Yeah. 4 factorial is 24, right? Divide by 8 is 3. Okay, and so on. So basically you can the other way to find the moments will be to match, okay? And of course, over here, you look at the terms, right? Like, for example, you don't have odd terms. Odd terms are missing here. And this can only happen if the odd moments, so it implies that the odd moments are 0, okay? Right, so, which means for the standard normal, it's odd moments, things like this. They are all 0, okay? Which you can actually find from this expansion. Okay. So so there are 2 ways to do it, right? Either you can use calculus, or if you are calculus, the this may be, it may look a little bit easier, but if you know how to use the Taylor series expansion, then usually this will be actually faster. Okay, but then so both are usable. Okay. All right. So once you know the moments, then of course you can find the variance. Okay. Now, first thing is the following. So ideally, well, moment generating function should characterize a probability distribution. Okay, which means if MGA, sorry, if the MGF is equal to so if MGF equals to E of t squared over 2, then the probability distribution is standard normal. Okay, so it's kind of like ideally we want something like this, right? There's a unique identifier for a particular probability distribution by just looking at the moment generating function, right? If you have the moment generating function equals to this form, for example, then you know that the distribution has to be normal 0, 1. It can't be other distribution. Okay, so this will allow you to characterize your probability distribution. But that's a problem. It turns out that some probability distributions do not have moment generating function. Okay, there are actually some probability distributions that do not have moment generating function. So the example, the classic example is the Cauchy distribution. Okay, the Cauchy distribution. So the Cauchy distribution is actually your t distribution with n equals to 1. Yeah, it corresponds to your t distribution of n equals to 1. And it basically looks like this. So it can be centered on 0, and it just has a very long tail. Right. So it's just like a hill that has very long tails. Okay, and its PDF is given by the following: pi 1 plus x squared. Okay, your x is in the real line. Right, so this is its PDF. Okay, so just for a few minutes, can you check that, can you verify that the moment generating function does not exist for the Cauchy? Just check that. Okay, take out your pen and try to see that you cannot find this. Okay, in fact, you will find that this is this is infinite, right? So it's not finite. Okay, so you don't actually have it. So just try to verify that. Okay, so let's look at this. So for the Cauchy, the moment is pi 1 plus x squared dx, right? Okay, in order to show that this is actually not finite, right? So what sort of strategy can we use? Anybody? So we want to show that this is, so in order to show that it does not exist, we want to show then that this is greater than some integral that evaluates to infinity. Okay. So how do we show this? Anybody has any ideas? After you have done all this exercise on using inequalities, so have you managed to develop some kind of maturity to think about such problems? Anyone?
Can use, is it okay if we use this integral is larger than we integrate etx from negative infinity to infinity?
You are saying this.
Yeah. Then we show that this is
But how would it be larger? Because
I think I have some.
It's always
smaller.
No, if you use smaller, then it cannot work, because if you use smaller, you were just saying, so okay, fine, it's bounded by this integral, and this integral is infinite. So you don't get anything that's tangible, because the most you will know that, well, is less than infinity. So how would this would not exactly meet your objective, right? So actually, if you intend to show this, now of course you can split it into two parts, right? This part is a little bit tricky because it involves negative, right? So, but it doesn't matter. You split it into two parts. You just have to concentrate on this part. Okay, as long as you can show that this part here is some integral and it already is unbounded, then your objective is done, right? So remember, this is the usual strategy of actually simplifying a problem, right? Break the problem down into sub-problems that you can solve. I mean, this is a recurring theme in, actually this is the kind of transferable skill that you can learn, that you actually get from mathematics, right? You know, all these theorems that you learn, you're not going to use them in real life, right? These are all theoretical, so unless you're doing academic work, you will find that once you get out of university, all these things will just get away from your life. But the whole point of this thing is that, you know, if you manage to observe this kind of pattern of thinking, right, then it helps you in general. It's a transferable skill, because then when you see some problem, right, you don't try to, you're not overwhelmed by it, because you know that, well, you can be, it just looks complicated, but if you know how to break it down to the sub components, and then work through with the subcomponents, then it is not that bad. Okay, so this is the general kind of training that we actually get from doing all this abstract stuff, right? I mean that by themselves, the abstract stuff don't really relate anything to your real life, but it's the way of thinking. Yeah, so you have to take note of that, right? It's the way you think about through it, right? That way of thinking is transferable, right? Once it becomes a kind of habit, yeah, then you will find that it makes a difference in the way you do work, right? Compared to people who never studied mathematics or have dealt with this kind of problems, right? It is very different kind of way of doing things. Okay. So anyway, so here this integrating this whole thing. Well, this integral looks really a little bit complicated to do. So, but then we are not trying to evaluate it, right? So don't do the brute force and try to kind of like evaluate it, and it'll probably be too difficult. Okay. So so we kind of like just kind of like this is not important. So we focus on this part, right? We want to show that so this integral is exceeds certain integral, right? And that integral is unbounded, right? So what can we do here? Anybody has some ideas? We'll try out ideas, yeah? Because if you just study like if I just write down the formula and then that, yeah, it doesn't really help your thinking because you don't see the process, right? And then it's kind of like pointless because if it's just a formula, then doesn't really you don't see the process, so you then you don't get the transferable skill, yeah. Just throw some ideas around. It's okay. The point is to be able to generate ideas. Your ideas may not be correct, doesn't matter. It's better than having no idea at all, yeah. Because when you generate ideas, you can stimulate discussion, and eventually you might be able to find something. Right? If you keep quiet, you don't generate anything, then that's it. It just silence. Everything is silent, right? Hmm. Anyone? Again, this may look actually quite difficult, but you can make it simpler, right? You don't have to evaluate the whole thing, right? Now, what can you do with the exponential function? So we want to say that this thing is greater than some integral. What is this integral? So I'm dropping you an idea here that you can get something out of the exponential function. I think we just looked at that 10 minutes ago. What can you do with the exponential function?
Taylor series expansion.
Okay. You have this. All right. So good start. Then from here, how do you construct some inequality here? Okay, it's a good start. Well, make use of what you know about the exponential function. The exponential function, you must always remember its infinite series, because from there it can actually lead to a lot of ideas. By itself, it's just some function, but once you see it in the terms of an infinite series, then a lot of possibilities become possible. Okay, so please do take note of that. Yeah, it's always a good start with the infinite series representation of some common functions. Okay, so you got to this stage. All right, then how would you proceed? So your exponential function is equal to 1 plus all these terms, right? Okay. Do you need all the terms? Anyone wants to give a suggestion?
Do we have a constraint like t is larger than 0? Wait.
Here, of course, you can just bound your t to 1. Okay, they just keep it like that. In fact, actually, you don't really need to bound it to 1. Actually, in this case, I think in generally R will do. That is just to make sure that this whole thing is convergent, all right? So the point is, if you're going to work with all these terms, there are too many terms here, so that is not going to simplify the problem. And you just need to deal with an inequality here. So from here, how can you construct an inequality based on this? series. The series has many terms. Therefore, it should be larger than 1.
Sum of all the even terms, because there might be a possibility that the tx, the odd element is negative, right? But the even element must be positive.
No, here everything is positive. If you choose your t, I mean, like, of course your t can be in R, so you can choose your t properly, right? So in this case, there is no issue of negative coming in. Because your x are all positive, if you t choose a positive t, then no problem. So you don't have to deal with the negative terms.
Is it okay that we choose 1? Because it's greater than 1 over the pi and 1 plus x squared.
Okay, let's try that. So if, okay, you're saying that this is greater than 1, right? Of course it's greater than 1 because you got these terms here, right? And these are all positive. So definitely larger than 1. So this will be this. And unfortunately, this is, well, this is finite, right? This is half of your Cauchy, so this is 1 over 2. So, but then you just know that it's more than 1 over 2. So you are not able to achieve your objective here. But it's in the right direction. So what should you do? So you're taking too few. You're not choosing the correct term here. You're choosing the term 1 here. What term should you choose?
dx.
Okay, let's try that. Definitely your ETX will be larger than TX, right? Because it's just one term here, so you got extra term, so it's larger. Let's try that. So this will be TX. Okay, what will happen now? So what will happen now? This is TX, fine. And your T is just some constant, so you can basically take it out, right? So basically you have this integral. So what happens now? What is this integral? Is it familiar, this integral?
The ln of 1 plus x squared over 2.
Okay, that's right. So
With the constant outside.
basically you have this thing here. So you can have over 2. So this is 2x over, so your pi can take out 1 plus x squared dx, right? And this part here is the derivative of this denominator, right? And we know from basic calculus that this integral will be log of 1 plus x squared, okay? When I write log, it means ln, okay? Right, I'm not, so log means ln, okay? If it's log base 10, the 10 will come out, right? So when I write log, it means ln, okay? So you have this thing, 0, infinity. Well, of course, you know the correct way to write this is you take limit m tends to infinity. This one is your m, right? Okay, but because strictly speaking, you cannot put infinity here because that's a substitution. You cannot substitute an infinity inside because that infinity is a concept, all right? So by right, you should take a limit, you put that. But anyway, I think most students will write it like this also. So anyway, just to let you know, okay. So then definitely this is infinity because when this term becomes larger and larger, the log is unbounded, right? So there you successfully show it. All right, so there, congratulations. So the trick here is to pick, there are many things that you can pick. In fact, I think picking this, the square term or this, the cube term will also work, right? But the simplest one that already works is this term, right? The tx, because then it will lead to the log, and that already will give you infinity, right? So yeah, this is the way to think about it. Okay, I hope you actually learned something from this kind of this illustration here. Yeah, the way to how to look at it and break it down to small problems, right? So you can see here we already broke to one part, so we basically don't want to care about this, right? We focus on here. And here we are trying to make some progress. It looks like, well, looks like there's nothing much you can do with this thing, but this part here looks like you can do something. So infinite series. And then look at the terms. Well, you don't need so many terms, and you basically like think about it in terms of what is it larger than, because we are trying to show that this is larger than something, right? So, well, you could try one, and that would not lead you to what you want, but then it's a good direction. So then you can say, well, what if I try the tx term, then what will happen? So immediately now you get what you want. All right. Okay. So yeah. So from here we can tell that the Cauchy for the Cauchy, the moment generating function is infinity, right? Does not exist. Okay, we cannot give it a finite form. So this means we have to, the moment generating function has some kind of limitation. Okay. By the way, your Cauchy actually has a infinite mean. Yeah. Its mean is infinite. You can check expectation of x is actually infinite. Basically, it's from here already, right? Yeah, expectation of x is infinite because basically this is just the expectation of x. Yeah, right. So Cauchy is one of those distributions where the mean is actually infinite. Okay, and because its mean is infinite, therefore its other moments are also infinite, because once your mean is infinite, your variance is also infinite, because the variance is the second moment minus the square of the first moment, right? So since your first moment already infinite, then your variance is also infinite. Okay, so this is one of the very kind of like a bit weird kind of distribution where the moment and the variance are infinite, right? The Cauchy distribution. Okay, so so because of this limitation of the moment generating function, we need to use something else, right? And this is where we have the characteristic function, okay? And the characteristic function will exist for all distributions, okay? And including the Cauchy. And just take a break now, and later take a 10-minute break, then come back, we will learn about characteristic functions, okay? Okay, so welcome back. So let's get started. So we're going to talk about the following, the characteristic function. Okay. All right, so let's define the characteristic function, right? CF means the characteristic function, okay? so so it's just very simple. And this is basically just a more formal way of defining it using Lebesgue integral measure. But for actual evaluation, we basically just rely on the usual Riemann integration. Right, the characteristic function of a probability measure mu on the real line is defined for real t by the following, like phi t equals to the integral. So you can see that it only differs from the moment generating function, right, with it. This I is a complex number, yeah. Okay. So basically, its only difference is that instead of using t, we have it, right, where I is the complex number. And actually, once you introduce a complex number here, strictly speaking, this integral is actually a complex integral. Okay, and unless you have taken a course in complex variables, which you are unlikely to have done so, right? Because that's a course in the mathematics program, and usually stat students don't take it. Then you will not know how to do complex integration, right? Complex integration has has a kind of theory that you have to study, right? And it is not as the way you do it as you you involve certain things called you integrate along certain contours rather than over certain intervals of values, okay? And you have to use some theorems in complex variable integration to work through that. So it's actually not really, so technically if we are going to do it, it is too time consuming, right? Because you have to go through some theory on complex variables. That will be like half a semester, okay, just to learn that. And finally learn how to do the complex integration. So what we are going to do here, generally what is covered is that in a lot of cases, sometimes where you can actually get by the complex integration by pretending that I is actually a real constant and use the Riemann integration to do it, and you will get the same answer as you if you use the complex integration, right? It's more like a kind of a hack. But in this case, since it leads to the same result, we are not too picky about that, all right? Because the alternative will be you have to, the alternative is that you have to spend half a semester to learn complex integration. And generally that is out of the syllabus for most people. Okay, so otherwise, if if you can't use the hack to evaluate the integral, then it will be given to you, right? Okay, so you don't have to worry about not knowing how to do complex integration. Okay. All right. Okay. So what's the advantage of the characteristic function? Right? It always exists. Why does it always exist? Okay. The reason is because your E of itx is bounded. Yeah. So so your E of itx, if you remember your complex variable theory from basic maths, so this is I think this is something called the de Moivre's formula. Okay, the expectation of some complex number here, right? So this is your real part. So this imaginary part. So it will be the cos t plus This is the complex part, and this is the sine t, the sine of this real term. Right? And when you take absolute of the complex number, basically it's taking the Euclidean. Okay, this two term, the Euclidean distance, cos square tx plus sine square tx. And from here, you know that it's 1 because this is a trigonometric identity, right? Okay. Cos square of theta plus sine square of theta is equal to 1. Right? Trigonometric identity. So therefore, the absolute of the integral e of itx fx dx. Right, so the absolute of this integral, which is bounded by okay, this thing is, so this is actually equal to fx, right? Dx, because the absolute, so you can write it as the absolute of eitx fx is basically, you can split it up into two parts, right? So the absolute here already gives you 1. The absolute of fx is definitely fx because fx is always positive, right? Your Prodi density function is a positive quantity. So then you basically have this, and this is equal to 1, right? Because you're integrating over all the support of fx, okay? So it's bounded by 1, yeah? Okay, so it always exists, right? So your absolute of psi t is bounded by 1, right? So it always exists. Okay, so it will work for all distributions. Right? Now, for the Cauchy, right? For the Cauchy, your phi t will be something like this: eitx minus 80 over pi 1 plus x squared over dx. This one you cannot find from directly. You have to use complex integration. Okay. And for complex integration, so it's not covered. So you can't actually do it, right? You cannot pretend that this is constant and get it. You won't happen. This one you have to do it in the complex plane, and this is actually a kind of like a limiting case in the complex integration. So unfortunately we cannot show this, but what we can show is that this one finally will be equal to some value here, which is the Cauchy. Okay, the Cauchy will be the following: minus t. Okay. So I think for this course, if you want to check this thing, you can use Wolfram Alpha. Okay, go to Wolfram Alpha, and you know, I think all of you know Wolfram Alpha. Is a website that where you can actually ask it to compute integrals and derivatives for checking. Anybody knows about Wolfram Alpha?
Yes, doctor.
Yeah, I mean, like sometimes when you do some assignments, you want to check some of your results. You can actually ask it, and actually it's actually it's very powerful. Okay, so you can actually put this in. Just tell it you want to do the integral of this function from minus infinity to infinity. This one I put the I. It is smart enough to know that I is a complex number, so you will get this result. Okay. All right, so that's the case for the call sheet, right? So let's look at some other examples. Let's say your X is uniform. Uniform 0, 1. Okay. So my phi t will be 0, 1 eitx times 1, right? dx. So this will be basically, so this one you can basically use the hack, you treat it as a constant. So basically you have eitx 0, 1. Strictly speaking, this is actually illegal because but it's just that it gives you the same result. Okay, so we kind of like do it, but with the understanding that strictly speaking, it is you have to use complex variables. Okay, so here you will have sorry, there's no x here. So this will be 1 minus e of it over it. Okay. Sorry, this will be the other way around. E of it minus 1. Okay. And sometimes this one, if you want to get rid of the I in the denominator, you can multiply with I. Okay. So you know that since I is square root of minus 1, so I square is minus 1. So there you will get minus t I e I t minus 1. Okay. So rearranging, you will get 1 over t. So you get I here, 1 minus e of it. Okay, still this can have some other expressions, such as you can write it in terms of trigonometric function. So that will be cos t plus I sine t minus 1 over it. So you can write this as, so the real part will be cos t minus 1 plus I sine t, okay, over it. So this one, in fact, you can get sine t over t, right? Then minus I of cos t minus 1 over t. Okay, so this is basically just rearrangement. Okay, like for example, of course it is this form, right? But you can rearrange it to get this form. Okay, by basically expanding using the Moivre's formula, right? So you get it in terms of real part. So this is a real part, and this is the imaginary part. Okay. Okay. So some of the characteristic functions, right? So therefore, some characteristic functions can be actually a complex number, right? Like in this case, the uniform. So you have a complex number as a you have a complex number as a kind of characteristic function. Okay. Whereas in other cases, they can be real. Yeah. So it's actually like both types. Okay. So let's look at some other examples. So you can also have examples in for example, like a Poisson, right? So these are basically nothing much. If you have a discrete, so your Poisson will be basically just, again, eitx, so summation eitx times the Poisson PMF. And basically this will be just take out IT lambda power of x, x factorial. So basically this is again just the infinite series for exponential function where the term is this, right? Multiplied by e of lambda EIT, okay? So you end up with e of lambda exponential IT minus 1, okay? If you contrast it with the moment generating function of Poisson with mean lambda, so parameter lambda, then it's the same, right? Except that you replace the t with IT, okay? All right. Okay. So you can also have a characteristic functions for discrete distributions. Now let's look at how to actually get moments, right, out of characteristic functions. Getting moments from characteristic functions, okay? Right, okay, so your characteristic function is defined as this. Okay. Now, so if you apply the like what we did just now, the infinite series, okay, which is your Taylor series expansion, right? Then you will get 1 plus ITX plus ITX squared over 2 factorial plus ITX cubed over 3 factorial and so on, okay? And basically this one is, if you write it down in a more compact notation, it will be summation IT power of n over n factorial, right? So yeah, just take note, right? So this one, right? So power of 2, 2 factorial, power of 3, 3 factorial, okay? So you have this. And then yeah, of course you have your x power of n. Your n is from 0 to infinity, okay? And of course, this one, you can move the expectation sign to be with the random variable because the rest are just basically constants, right? Factorial e of x power n. Okay, now if you take derivative with respect to t, right? What will you get? Okay, so when you take derivative with respect to t, basically you so this is kind of like a more compact representation, but well, actually you can work on this as well. So this will be, you differentiate here, right? So you will get I can add I power of okay, never mind. So t power of n minus 1 . So you get n over n factorial . So this will become, so this will cancel, right? And after that, your n will start from 1, okay? N power n t n minus 1 n minus 1, right? Okay. And if you let your t to be 0, so what's going to happen is that, except the first term, right? If you look at this part here, the first term, your n is 1, right? So your basically, this is, you will get I power of 1. Okay, then this is 1. So over 0 factorial, right? Then expectation of x. Plus some other, plus 0, because the other terms, right, they will have the t that is starting from t power 2 and so on. But since you set t to be 0, so they all turn to 0. Okay. So basically over here is just the first term. Yeah, you're taking the first term. All right, the first term of this sum. Okay. So basically, therefore, your expectation of x is given by the first derivative of your characteristic function divided by I. Okay. And from here, you can basically work out, right? From here, you can continue to do second order derivative. So you differentiate this one more time and so on. You will find that your expectation of x, right? If you differentiate k times, it's basically just you differentiate your characteristic function k times, set t to 0, and then you have a divide by I power of k. Okay, k is 1, 2, 3, and so on. All right. So basically, to find the kth moment, right, from the characteristic function, you basically is almost the same as your moment generating function, except that you basically differentiate the characteristic function k times, set t to 0, and then you just have to divide it one more time with the complex number I raised to the power of k. Right. So it's very easy to remember. All right. So let's look at some examples of using this result. Yeah. So let's say my x is standard normal 0, 1. So what is my e of EITX? So just now we had e of IT squared over 2. Just now for moment generating function, we had of normal 0, 1, we had t squared over 2, right? So basically over here, we just need to replace the t with IT, okay? And basically this will give you e of minus t squared over 2. This is my phi t. So if you differentiate it once, set to 0, so that will be differentiate this thing, right? So minus t e of t squared over 2 evaluated at t equals to 0. So this is 0. Okay. Therefore, the first moment is this, right, which is 0. And the second moment, so you have to differentiate this guy here, right? So, so how do you differentiate this? Now, this is a little bit. Let's try to use some. Try not to work with this form, but we can write it like this. So this is basically the derivative of minus of t. Now this thing itself is phi t, right? Okay. Again, let's look at this. This is phi t. We write it like this so that we can actually recycle the result for the first derivative, all right? So you'll find that this is much easier to do rather than you treat this as a different function. So basically this one becomes minus t times the derivative of phi t plus the phi t times derivative of t, okay? And because here you have evaluation at 0, okay? So basically then you will have, this part it will be 0. So you basically have minus phi 0, okay? Much easier to do than, let's say, if you apply the derivative on the product, that will give you headaches, okay? So then you will get this thing, right? And this is basically just minus 1, okay? Because phi of 0 is 1, yeah? Right? When you sub in t0, so you get 1, okay? And therefore, the second moment is basically the second order derivative of phi, which is minus 1 over I squared. Okay, that gives you 1 because I squared is minus 1. All right, so the second moment is 1, which is correct because our variance is 1, right? Okay. Yeah, so your mean is 0, so your second moment is equal to the variance. All right. So actually, quite easy to use. Okay. Okay, so I think that's all I want to talk about characteristic function for up to this point only. Okay, for today. So next week we can look at a few more examples and then we are done, right? Okay, so that's all for today's material. Are there any questions from you? Right, okay, so I think, okay, so any more questions you can, if you think of them, you can ask the next lecture, all right. Okay, so that's all for today. Thank you for listening. So I'm going to stop the recording now.